Okay, good morning, everyone. End of the week. Still no resolution for next week. Just want to let all of you know that I will hold classes as usual. You can come in person to campus or you can attend online, your choice. Um, not usually, I typically commute via North County Transit bus. And I have no idea whether the buses will be allowed to enter campus or not. I hope they do. Otherwise, they will stop somewhere off campus and I'll just have to walk or hike in. But I don't foresee a problem in me reaching here before 9 o'clock. But if I am late, if I'm not here at 9 or 9:10, that's the reason. But I will hold class as usual. Okay. If you have made plans to go home for the week, again, standard rules apply. You can attend class online or you can, just watch the lecture video later on. It's a Monday, so we will have quiz as usual. Quiz number 2. Quizzes are always based on the material that we have done in the preceding week, meaning the material that we learned this week. I will not specifically test students on the previous material, but the previous material knowledge is required to solve for certain things, right? I mean, we learned about Ohm's law and KCL and KVL, so you might have to apply those to some of the problems. I won't specifically test you on Ohm's law or on KCL or KVL, but it's something that students should be aware of. Make sense to everyone, right? So again, quizzes will always be on a Monday, first thing when you reach the class. And then the material tested is always the material that I covered in class for the previous preceding week. Okay. So again, announcement for next week, we'll have class as usual, Monday, Wednesday, Friday, unless something else happens and I'm unable to come or something. But that's my plan. Any questions? Okay. All right, moving on then. Let's see. We stopped. New share here. We learned about resistors in series, resistors in parallel, then combining a large network of resistances and reducing them down to one single resistor. And then we introduced a source in there. We looked at a voltage source as an example problem. And then we looked at 3 different examples, one of which had a current source. So no matter what the source is, whether it's a voltage or current, you simply apply Ohm's law, V equals IR. You take the large network of resistors, reduce them down to one single resistance. So you have R. And if the source is a voltage, you have V. You can calculate the current flowing in the circuit. If you have I as the source, then you can calculate V, the total voltage appearing in the circuit. And that is what we did in example number B. Right? That is what we did in example number B. There was one technique that I wish to show here in equivalent resistance. Let's go back. All right, this is as good a point as any. It's a technique that I don't know, I somehow developed it. I have not come across this technique anywhere in a book or from any other person. There might be other people using this technique, but it's relatively straightforward and simple actually in its application. If you are trying to find the equivalent resistance between any 2 terminals in a circuit, doesn't matter what that circuit looks like, what you do is you take, so let's take a look at, let's take B. Okay, let's take B. I'm going to draw that circuit out here first. These are terminals A and B. And then, let's see, resistor. Okay. And then R1, R2, R3, R4. So this is R1, R2, R3, and R4. So we have 2 terminals where we are trying to measure the equivalent resistance, right? So in this technique, what you're going to do is you will draw two lines spread far apart. These lines basically represent the terminals A and B. These are your measurement terminals. So you draw two horizontal lines and give enough space between the lines to draw out all the resistors. The goal here is to draw all the resistors vertically or maybe even horizontally if you need. Okay. So that's the first step. Then we start at terminal A. What resistors are connected at terminal A? If you look at this node, specifically the top node right here. So we have two resistors, R1 and R2, right? So we drop R1 vertically right here. Then we also have R2 connected at A. So we drop another line for R2. Leave a little bit of space between because we don't know how the circuit is going to turn out. And depending on how many resistors you have in the circuit, you might need more space. So two horizontal lines at first, noting the two terminals of measurement. Then we start at the top node and we draw out the resistors that are connected to that node. So far we have R1 and R2. Then we follow R1 to its end. Where is R1 connected? To terminal B, right? Everyone sees that? So we simply extend R1, go all the way to B. And we are done with R1. Then we take a look at the far end of R2. What is at the other end of R2? Which is the top right node right here. So at that junction, we have R3 and R4, right? R3 and R4. So this is what I'm going to do. I have a junction. Again, the goal is to drop all the resistors vertically, kind of like hanging from the top. So I'm going to draw out R3 and R4. That takes care of that node, right? That node is gone. Or not gone, but done. So far, so good. Is everyone with me? Okay, so since this node is done, then we go to the other end of R4. Where is the other end of R4 going? It's going into B. So we connect it all the way to B. Then we have one more connection left hanging. We go back to R3 and we note that R3 is also going to B. So we drop or extend R3 all the way to B. Have we accounted for all the resistors in the circuit? Yes. And that's it. Now you look at the nodes and the connections and you determine which resistors are in series and which are in parallel. And this technique works for almost every circuit that I've tried it on. Okay. Now, having said that, there are some circuits that cannot be reduced. Okay. So if that circuit cannot be reduced like manually like this, then of course this technique will not work. But if the circuit is reducible, doesn't matter how the schematic is drawn, this technique, you apply to it and it will work. So there's a problem. There are a couple of problems in the homework that you will encounter which have that diamond shape, right? 4 corners. And you apply this technique and it will work out. So if you take a look at this, R1 is between A and B. Right now we leave it hanging, right? It's one single branch. Then we take all the other branches that are there in the circuit and we reduce them down to one single resistance. Because after we reduce it to one resistor each, basically reduce each branch, no matter how many you have, reduce it to one single resistor. If you reduce it to one single resistor, then all of them at the end would be in parallel. right? So you tackle each branch individually. So since R1 doesn't have anything, we leave it alone. We go to the second branch. In the second branch, we see, what do we see? We see that R3 and R4 are in parallel because they're connected up top, they're connected at the bottom. So R3 and R4 are in parallel, which would then be in series with R2. And that, let's mark it as R5 or R6. And then we have R1. Actually, let's stick with the convention that we used in the earlier solution. So we call this R5. We'll call this R6. And then final answer for REQ between A and B is R1 parallel R6, which is what we obtained right here. Let's take a 10-second pause. Let it sink in. Let me know if you have any questions. Again, the goal is to get every single resistor in there vertical. Okay. Does the technique make sense? Okay. Again, as I said, there might be many people out there who might be using the same technique, but I've not seen it in any textbook, nor have I come across any person who uses the same. Okay. Moving on. Were there any questions about series parallel equivalent analysis technique? Is everybody clear on the steps? We already did last class. Oh, you're talking about C. Okay, got it. All right, so C, I think I assigned for practice, but let's go read in class right now. So we have 4 resistors, R1, R2, R3, R4. We're talking about example number C. Let me draw the circuit down here. Do I have this correct? Yes. Then we have a voltage source, plus minus. Vs is 30 volts. And what do we have? R1, R2, R3, 10, 15, 40, and 25. Okay, 40, 25, 10, and 15. Current directions are already given to us. So this is I1, I3, and I2. So we don't have to do any assumptions in this case. Okay, so the question being asked is calculate all the voltages. Well, the question in the example simply asks you to calculate the currents. We can find the voltage as well as the current. All right, let's scroll. Okay. So first things first, voltage supply. Current for the supply goes from minus to plus. Current goes in this direction. And of course, that's the same current as I1. So once we find the total current flowing in the circuit, we know that total current that being supplied is I1, which is going through R1. Now we remove the source. and we reduce the network of resistors down to one single resistance. And so my open terminals are here. I'll label them A and B. This is the setup of the problem, right? So this is something I would want students to show me in the quiz or in the exam. Okay, source is removed. I want to find REQ between A and B. For those of you who log onto the class notebook, can you write on the annotations that I make on the slides? I believe it's not possible, right? You can only view it. But can you copy it and write it in a separate part of the notebook? I wonder if things have changed or they're pretty much the same. Okay, so that's a feature that's still not there. All right. Okay, so starting at the farthest end, we have R4. We start reducing the circuit as we move towards A and B. So R4 and R3, series or parallel? I have one answer. Anyone else? They're only joined at one terminal, not two. So if it's one terminal, then it's in series. So R3 is in series with R4, and I'm simply going to write out the equation directly. So REQ is equal to, starting at the farthest end, R4 plus R3. The series combination of R3 and R4 would be in parallel with R2 because they are joined at the top and the bottom node. So this would be in parallel with R2, and that combination of three resistors would be in series with R1 because it is joined at the top node right here. And so I would say plus R1. Then simply plug in the values and solve. So R4 plus R3 is 40. 40 in parallel with 40 should give me 20 plus 10. So REQ is 30 ohms. I like the examples in the book because the values are given such that they come out like round numbers. And they're easily calculable values. Of course, real life never works that way. So real life, the numbers would be all over the place. Make sense? Right? So 30 ohms. So now my circuit is, I'll go from here to here. This is a marking. I will plug the source back in. Plug the source back in. And now my REQ, 30 ohms. VS, of course, is also 30 volts. So I can calculate my I, applying Ohm's law. Don't even need a calculator for this. I would be equal to VS divided by REQ equal to 1 amp. Be good? So now we found I, that is the total current being supplied by the voltage source VS. Now we expand the circuit in the exact reverse order. So if we expand the circuit, I know I1 is equal to I, so that is 1 amp. Now, when we get to this point, I1 splits into I2 and I3, right? We simply need to find I2 and I3. I can find the voltage across R1, apply KVL and find the voltage across R2, or I can find the direct voltage across R2, R3, and R4. Multiple ways to solve for the same thing, right? As we saw in other examples. Question? Yes. That was going to be my next point. So methods, right? But then intuition, simply as we saw in the other problem, the current source where we had 5 plus 15 and 10 plus 10. Current is divided equally between two resistors because both resistances have the same value. So R2 is 40, R3 and R4 gives us 40. So we can solve it simply by applying current division. We can say current I1 splits in two equal halves, and that's it. So I2 would be equal to I3 because, or since, R2 is equal to R5. Actually, I never said R5, but by the way, how many of you recognize that symbol? It's an upside down, therefore. The symbol means because or since. Like therefore is a triangle pointing up. This symbol is a triangle pointing down. So I1 is equal to I3 because R2 is equal to R5. 40 equals 40. And so the current splits equally. Doesn't matter what the resistance values are, but the current would split equally. And so I can write I2 equals I3 equals I1 divided by 2. Gives me 0.5 amps. And once you have the current flowing in both parts of the circuit, you can simply calculate the voltages for the three resistances. Well, for all four, actually. 40 times 0.5, 20, and 10 times 1 is 10. 10 plus 20 is 30 volts, which is the voltage that is being supplied by Vs. So you can do KVL, you can do KCL, you can apply Ohm's law, you can apply plain logic to solve this problem. Example B was the exact same way. You had a 2 amp current source being split into 20 and 20 ohms, or split across 20 and 20 ohms. All right, 10-second pause. Let me know if you have any questions. Any questions at all? Okay, moving on. Voltage division and current division. Now we just saw in example B, and in this example C, we talked about how current is going down a pathway and then it splits. It splits in two, right? If it's a parallel connection, it splits. It comes across a junction and it splits. It's like a fork in the road. Okay, there's a there are two or more pathways for the current to flow through, so it splits according to the value of the resistances. The same thing happens for voltages. If you have a current flowing through a series connection of resistors, a voltage drop appears across each resistance. And a voltage drop appears across each resistance, that voltage is directly proportional to the value of that resistance. All right, so let's see how that comes to be. Again, I'll do the derivation, but the derivation is not important. What is important is how you can apply the voltage division principle. So the voltage division principle is again derived from Ohm's law. but it simply allows you to calculate the voltages directly by skipping over a couple of steps. Okay. Has this been covered in physics? So some nods. Okay. All right. So we have a voltage supply, V total, current flowing in this direction, I, and of course it goes through all three resistances. There's no other pathway for the current to flow through, so the same current I flows through R1, R2, and R3, right? So if I was to write the equation for Ohm's law, first thing I would do is find Req, which in this case would simply be R1 plus R2 plus R3. So I would simply be given by V total or VT divided by R1 plus R2 plus R3. Then if I want to find VR1, VR1 would simply be I times R1. Then you plug in the values and you have VT R1 plus R2 plus R3. Actually, you know what? Rather than keep doing R1 plus R2 plus R3, I'm just going to write it as Req. Req. That's it. That's the derivation. Remember what I said in the definition, right? Voltage division principle states that when you apply a voltage to a series connection of resistors, a fraction of that voltage appears across each resistor. And that voltage drop, that fraction, is simply given by the value of the resistor to the total equivalent resistance. So VR1 is a fraction of voltage VT. Okay, VT. And that fraction is given by that resistance R1 divided by the total equivalent resistance Req. The equation is much straightforward and simpler rather than using the words. So voltage across R1, VR1 is VT times R1 divided by Req. Similarly, VR2, even without doing any derivation, I can write VT times R2 divided by Req, and VR3 is VT times R3 plus Req. That's it. Applying voltage division is very straightforward. It's a fraction of the total supply voltage. Fraction is given by the resistor R1, R2, R3 divided by Req. All right, 10-second pause. Any questions? Make sense to everyone? Now, voltage division can be applied to any number of resistors. As long as they're all in series, it does not matter how many resistors you have. Okay, current division is a little bit more complicated than that. But does this make sense? Right? When you have a voltage across series connection of resistors, you simply apply this equation, and that's it. You can have this on your equation sheet. Okay, so if in an exam or a quiz, I ask you to solve using voltage division or to solve using current division, you have to use this technique. You can sit there and you can derive this if you wish, but you should know how to apply this directly. Okay. What is the REQ? Easy enough. 1 plus 1 plus 2 plus 6, 10. So REQ is 10 kilo ohms. First use of the unit prefix, 10 kilo ohms, 10K. So in electrical engineering, when we refer to a resistor, we just simply stop at K. I don't know why. It's just become standard accepted practice. So we say a 5K resistor or a 10K resistor. So REQ is 10 kilo ohms. V total in this case is 15 volts. So if I apply voltage division directly, I can write VR1 is equal to VT times R1 or REQ. Therefore, VR1 is 15 volts times, what do we have? 1K divided by 10K. So basically 0.1. 1.5 volts. VR2 would be the same as VR1. So 1.5 volts. VR3 would be VT times R3 or REQ. So that gives me, actually, let's write it here. 15 times R3 is what? 2. Without calculating, what do you expect this number to be, even before we went to that equation? It would be 3 because 2 is twice as much as 1. So if a resistance is twice as much, the voltage would be twice as much. So even without writing out the equation, we should be able to see that. How about 6? 6 times as much as 1K. Directly proportional. Voltage division, again, voltage appearing across each resistor is directly proportional to the value of the resistor. So if 1 kilo ohm causes a voltage drop of 1.5 volts, 6 kilo ohms should cause 6 times as much as 1.5. So even without applying voltage division, you should know what answer you would obtain. But since we are teaching voltage division, I'll write out the entire equation. It should arrive at 9. Oh. And of course, when you sum it all up, it should add up to 15 kVL. 9 plus 3 plus 1.5 plus 1.5 rounds up to 15 volts. Make sense? Right. Now, when you do larger, actually, let's take a pause. When you finish writing it down, let me know if you have any questions. When you're solving larger circuits, it may not always be a source. It may simply be in a different part of the circuit where you have a voltage appearing and then you have a series combination of resistances. So it will not always be a source that is being divided. Okay. If we go back and we look at this circuit, those are in series, right? So if you find, or if you determine the voltage at this node and the top and the bottom nodes, that voltage is being applied to a series combination of R3 and R4. Everyone see where I'm going with this? Right? So it's not the source, it's the voltage that appears across the top and the bottom nodes right here. That's applied to a series combination of R3 and R4. You can apply voltage division and calculate the voltages that way. So again, I'm trying to get students to think about how you can apply small techniques to a smaller part of a large circuit. Again, remember, these are all tools. All of these circuit analysis techniques are tools in your toolbox. You can choose how and where, which tool you wish to use. Okay, unless specifically stated in the problem itself, you can determine which method you would like to use. All right, any questions about voltage division? Yes. Yes. So the question being asked is, the voltage the same for R1 and R2? And the answer is yes, because they have the exact same value. No, it doesn't matter. As long as it's in series, it could be anywhere. It could be right here. So again, circuit schematic can be drawn any which way we like. So right now we are drawing R1, R2, R3, R4. They're all in one line. We could draw the exact same circuit. R2, R1, R6, R3. Electrically speaking, doesn't change anything. Yeah, it's still in series. So R2, R1, R6, and R3 are still in series. So it doesn't matter how, in which order they are connected. Electrically speaking, they're the exact same thing. Does that make sense to everyone? So it doesn't matter where they are connected. As long as they're in series, it doesn't matter. Okay. Moving on to current division. Current division's not so straightforward. Current division applies. There are like 2 or 3 different techniques. I will show you one. I have a current source, I total, which causes a voltage drop to appear across that parallel combination of 2 resistances, R1 and R2. Okay, R1 and R2. You could apply Ohm's law and solve it that way for each resistance. We'll just derive it very, very quickly. So Req in this case would be R1 times R2 divided by R1 plus R2. Okay. We'll leave Req on the side for now. It's a parallel combination of 2 or more resistances. If it's parallel, they share the exact same node, meaning the exact same voltage appears across all resistors. Whether it's R1, R2, or R3, R4, R5, R6, R1000, as long as they're in parallel, the voltage that appears across the 2 terminals is a result of all of those resistors working together. And hence, the voltage that appears between those 2 terminals would be exactly the same for all resistors in that network. So in this case, voltage V appears across the current source, I, also appears across R1, also appears across R2. I can simply write from Ohm's law, V would be I total IT times REQ. And then I can write I1, applying Ohm's law again, would be V divided by R1. V in this case is IT to REQ over R1. Yes. So this will work with multiple resistors in parallel, but because they are in parallel, REQ is not as simple or as straightforward as just summing everything up. So if we substitute REQ in there, we get R1 times R2. That's the next step. So I1 would be equal to IT, and in this case, REQ is R1, R2, R1 plus R2, R1. R1 and R1 cancels out. So what we are left with is IT, total current flowing in R2 divided by R1 plus R2. And this is the reason why I said it would work only on 2 resistors. So if you wish to apply, I'll wait until everybody finishes writing. Okay, so if you wish to apply from the Ohm's law, then you find REQ for the entire network. And then you simply apply Ohm's law and find it that way. IT is REQ or R1, right? The resistor that you wish to find the current for is now in the denominator. It's not in the numerator. In voltage division, it was R1 divided by REQ. In current division, it is REQ divided by R1. When we plug in the values for REQ for 2 resistors, this is what we get. The current that appears or that flows through that resistor R1 is a fraction of the total current IT times that fraction is given by the value of the other resistance, which is R2, divided by the sum of the 2 resistors. So I1 is a fraction of IT. That fraction is given by R2 divided by R1 plus R2. As I said, slightly trickier than voltage division. In voltage division, we have REQ. It's straightforward, R1 plus R2 plus R3. So we can simply write it's R1 divided by R1 plus R2 plus R3. Finding REQ is easy enough. In current division, REQ is not straightforward. So if you wish to apply current division directly, you need to have 2 resistors. So you can either do this, or in my 201 classes, I just say just use this. Find REQ. When I say this, I would say use this. Find total REQ in the circuit, whether it's 3 resistors or 4 or 5 or 6 or 1,000, doesn't matter. You find the total equivalent resistance for all parallel resistors. So you find REQ, simply apply the equation in that box. I1 is IT times REQ divided by R1. Make sense? This is kind of the straightforward, and I would say easy way. This is, well, slightly more complicated. So again, you can have these equations in your equation sheet, but you should know how to use them. Okay, you do not need to know how to derive them in an exam, but you do need to know how to apply them. All right, 10-second pause. Yes. Any questions? Yes. Yes. Then it's only 2. So the question being asked is, can the box be used for infinite resistances? And the answer is yes. Infinite resistors. This actually applies. So if you had a parallel network of resistors, if you wanted to apply current division directly, you'd have to reduce. You take that resistor of interest, R1, you take it out separately, and then you reduce all the other resistors down to one single resistance. So you'd have to find Req anyway. So that's why I said it's easier to apply the equation that's in the box rather than applying the equation that's at the end. Yes. No. So it would be Req then would be what? R1, R2, no, R1, R2 plus R2, R3 plus R2, R1 divided by something. It'd be completely different. It'd be 1 over R1 plus 1 over R2 plus 1 over R3. And so Req would be completely different equation. The only reason it turns out this way is because if it's 2 resistances, then it simply becomes R1, R2 divided by R1 plus R2. So again, as I said, it just gets too confusing for a 201 class. And so I always suggest to students, simply apply the equation IT is IT times Req or R1. And that's it. Yes, but we still have to find Req. So if it's more than 2, let's say you have 3 or 4, you'd have to take R1, and then you have R2, R3, R4. You have to find Req for R2, R3, R4, combine it into one single resistance. So you have to do that work anyway. So why not just add R1 and find Req that way? So yeah, exactly. So again, this is a technique. It's in the syllabus, so we are required to teach it, and so I do show it to students. But then I also like to explain at the same time that the equation in the box, that's the most straightforward approach. Just apply it that way. All right. Let's see. We have a couple of minutes left. Let's do an well, there's the 3 resistors right there. Actually, we are almost out of it's 9:59. So all right, let's stop here today. We'll pick up here again on Monday. We'll have a quiz on Monday again. I won't have voltage division as part of the quiz, but reducing a network of resistors down to one single resistance and then applying series parallel equivalence. That is what we will test on. I will post on, I typically post, last time I sent an email to the class, but what I do is I typically post on Canvas under announcements. So every time quiz, the topic under test or topic under assessment, the prep work and the prep, what you need to study. So again, look for it under announcements on the Canvas page. Class as usual on Monday. I'll keep you posted about any new developments as and when I find out. Okay. Because I'll wish you all a good weekend. We'll see you Monday in 3 days. Yes. You can solve this by logic, by the way. 10, 30, 60. This resistor is 6 times as much as 10, 3 times as much as 10, and 15 divided in that proportion. All right. I'm going to end the meeting, then take student questions. Yes.